Okay, let's start with our acid-base POGIL. How do acids and bases behave in water? So, read through the why to talk about why acid and bases play an important role. It also talks about what happens when they're dissolved in water, and we call them aqueous. It also talks about the scientist here, Ranius, who came up with the idea of defining acids and bases by what their signature ion was for it. And that's what we're going to use in our table right here. So our model one not only has our acids, but it also has bases down below. And then it tells us what their common name is when it's aqueous. It tells us its chemical formula. It's found in what? And then these are the properties we're going to use. How does it taste? What does it do to litmus? And does it conduct electricity? So let's get started. What does it mean to be aqueous? So we read in the background, or we remember from solutions, if we have something that is aqueous, it just means that it's dissolved in water. So follow along on your POGIL as we go through it. Now it says refer to model number one. Now I just cut off the back end because we're going to focus on acids first. So what's the chemical name for vitamin C? So we'll find that vitamin C is here, and then when we look for its chemical name, we'll see that its common name is also ascorbic acid, which gives us a pretty good clue of what its classification is. Now, is vitamin C classified as an acid or base? We would see it's not only in its common name for an aqueous solution, but we can look at the final column too. Now it says examine the properties, so those are right here, and list 3 properties that all acids have according to model number 1. So I would say that our first property is that they all have a sour taste. Our second property is they all turn litmus red. And then our third one, we could talk about they all conduct. And that's because of those free electrolytes in the solution hitting our conductivity meter. Now, flip to page 2 of your POGIL. Examine the formulas for the Arrhenius acids in Model 1. What does each acid have in front of their chemical formula? So we're focusing in on here. We see that we have all our acids, the first 4 there. We'll see that it has an H in front, an H in front, an H in front, an H in front. We also read this in the Y in the beginning part of it. So what does each acid have in front of their chemical? H, are also known as hydrogen. So that's a clear indicator that it's an acid. Now let's focus on bases. So notice that I just cut the chart to only focus on the 4 bases down below. Now examine the properties of the Arrhenius bases in Model 1. List 2 properties that all bases have according to it. Now if we look at how they taste, one says bitter and it also says poison. So there's not a direct one like our sour for acid. So we're actually going to use these 2 as our properties. So if we have litmus, it's going to turn it blue to let us know that it's a base, so B and B. And then they can conduct electricity. The same thing as acids. Now it says examine the formulas. So our formulas are in this tab right here. What does each base have behind? So we have our metal, and then we have something behind it. We'll see that each base will have an OH. Now, how do we find out its name? We look to its common name in aqueous solution. So notice it says magnesium, and then OH is hydroxide, aluminum hydroxide, barium hydroxide, and sodium hydroxide. Now, a student dissolves a small amount of baking soda into a beaker and puts a piece of litmus paper within it, and it turns blue. Is the baking soda solution an acid or base? So if it turns litmus blue, we would see that baking soda is a base. So now, you have to go through and read this. Now, Arrhenius said that there's going to be an H in front, but we can classify an acid by how many H's and then eventually figure out how many reactions it goes through. So we're using our prefixes again. If it has 1 hydrogen, we call it monoprotic. Now, we call it protic is because hydrogen only has 1 proton if we remember from our atoms unit. If it's diprotic, we're going to see that there are 2 hydrogens. And if it's triprotic, we're going to call we're going to see it has 3 hydrogens. So the tiny subscript below the H lets you know whether it's going to be mono 1, di 2, or tri 3. So you might want to highlight that in your POGIL as you're going through it. So decide whether the following examples are monoprotic, diprotic, or triprotic. So I highlighted my H's to make it clearer to see that I'm only focusing on them and not anything behind it. So we'll see that H, just one, would be monoprotic. H2 of B would be diprotic. H3 would be triprotic. HF would be mono again. HCl would be mono. H2 would be di, and H3 would be tri. So that lets us know a specific type of acid and how many reactions they'll go through, is whether it's monoprotic, diprotic, or triprotic. Now our extension, some substances can actually behave both as an acid and base. They're called as amphoteric or amphiproduct. Water is one of these substances, so depending on the strength of the other substance, it can act as an acid or base. So give an example, water. Ammonia is also another one. NH3 can go both ways, depending if it's put with something else. So now, our final part of page number 2 is naming bases. What makes bases unique and how are bases named? So what do all strong bases have in table 1 in common? So if we look at our strong bases, what do they have in common? If we go back to our properties, we see they all have a hydroxide or they have an OH group with it. So notice it's Li is metal and then OH, 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 OH. So what is the name for the anion OH1? It is hydroxide. Now, we show the O first because of bonding, but we name it hydro oxide. Hydro has the H, so that comes before O in the alphabet. Now, this is the end of video number 1 on pages 1 and 2 of your POGIL. I hope to help you go through it. Stay tuned for the next video.